Hi everyone. Today we will continue our lecture on X-ray diffraction. So before we proceed, I will like to review what we studied in the last lecture. Okay. So in the last lecture we saw what are X-rays, how X-rays are produced. We discussed about the characteristic spectrum which gives rise to the monochromatic nature of X-rays, right. Then we also saw like how we discussed about the crystal systems, right. And we ended our discussion on that. But before we proceed, I will just again review basics of crystal systems, right. So we are talking about the periodic arrangement of lattice, right. You have a long range order in crystals, right. So first thing we looked at was the unit cell. So here what you see, you have this unit cell and it's arranged in 3 dimension, right. So it's a crystal, right. So what first we looked at only unit cell, right. So we defined unit cell by 6 different parameters: length along A, B, C axis and interaxial angles alpha, beta, gamma. So there are different classes, right. We discussed here, these are 7 different classes, 7 different crystal systems. Also now it is important is, and we discussed about the symmetry, right. So you can have reflection, everyone is clear, right. You can have rotation axis, right. You can see how we have a 4-fold symmetry in cube, 3-fold symmetry, 2-fold symmetry, right. And then you have inversion center, a rotation inversion symmetry. So basically these symmetry operations are used in crystallography, and the different symmetry operations acting through a point are termed as point groups. Okay. So there are 32 point groups, basically 32 symmetry operations, like in 3 dimensions, right, 3 dimensions. So now when you apply, so you know about the unit cell, now you have to apply these symmetry operations, that is what will give you a crystal. Now we are talking about the real crystal structures, right, those are the geometric manifestations, right. So the atoms of crystals are set in space in some fixed relation to the points of a Bravais lattice. We know there are 14 Bravais lattices, right. Now the atoms of a crystal are set in space in some fixed relation, right. See, some fixed relation means could have symmetry, okay. And the atoms of a crystal will be arranged periodically in 3 dimensions, and that this arrangement of atoms will exhibit many of the properties of a Bravais lattice, in particular many of its symmetry elements, okay. So and space group defines the entire spatial arrangement of a crystal system. Now you have a unit cell, it is getting repeated. So this whole, the space group defines the entire spatial arrangement of a crystal system. What you see here, basically what you see in A, right, you have this 1-dimensional lattice, it is a 1-dimensional, right, in this direction with unit cells marked by vertical bars. So you have unit cells marked by vertical bars. So you have one unit cell, right, it is a straight 1-dimensional lattice, one example, right. Now you can add some features, right. So in the B, what do you see in the B? This is again 1-dimensional lattice, okay, but you have this dash and dot. Dash dot, you can think of it as repeating features. These are the features which are getting repeated. Also we call these motifs, that is another it, but simply you can think of it as repeating feature. So it is getting repeated. So here you have dash dot, dash dot, dash dot, dash dot, clear? So this is 1-dimensional lattice, and this is a feature which is getting repeated, okay. Showing 1-fold symmetry, also it has 1-fold symmetry. 1-fold symmetry means, you know that if you rotate this by 360 degrees, it will bring it to self coincidence, right. You can try, right, it will, until you rotate it to 360 degrees, you will not get the same feature, It's clear. Now let us look at C. C, now the repeating feature is dash dot dot dash, clear. That is one cell. Again these dashed lines are one unit cell. So this feature is getting repeated. Is it clear? This is again one dimensional we are talking about, right. These are the features. So what's now also what you notice, you have three representations. So what we discussed, you see the unit cell and you see this repeating features dash dot dot dash, dash dot dot dash, right. So think of these as mirror planes. Okay. So you have one, these are the mirror planes, right. So think of a reflection. So that is one kind of symmetry. Now if you come back to see, we have the same pattern, right, we have the same pattern. Now in the last one, the bottom one, what we see, two-fold axes, two-fold axes. What does that mean? Two-fold axis means if you rotate by 180 degree. So see, so you have this dash dot dot dash, right, and these are the symbols for two-fold symmetry, two-fold axis, right. So you can try. So basically if you look at this, if you rotate it by 180 degree, you will get the same, right. Can you see, can everyone see that two-fold axis symmetry, right. So in this you now see that two-fold axis symmetry is there. In the middle one you see just mirror planes, right, the same arrangement, okay. And the last one, the D, in the D what we see, one dimensional lattice again with a basis consisting of two dash dot motifs. See, basis is also motif, right, basis is basically the repeating feature. So you have dash dot dash dot, this is the feature which is getting repeated. See, in crystal what you have, periodicity, right. So now you will appreciate, see, it's, we know about the crystal systems, 7 crystal systems, 14 Bravais lattices, but it is also important to consider the symmetry, the way they are arranged. In real crystals, when you apply those point groups or 32 points groups we have, symmetry operations on these Bravais lattices, then you will get a lot of space groups. So in reality you have only 230 space group, unique space groups only, not more than that. That is because of these symmetry operations applied on these Bravais lattices in 3 dimensions. Simplest case is when this unit cell is getting repeated, that is easy to visualize. But now from this you can see how this symmetry plays a role, right. So we will not go in detail because in itself this crystallography is a vast area, but just wanted to touch upon the important principles like what is unit cell, right, what is symmetry, what are the different crystal systems we have, right, so that we can then use that to understand the material. So we are talking about now real crystal structure. Simple ways, one we learned about BCC, body center cubic, right. Simple way of arranging atoms would be just put the atoms the corners, right. You have the BCC and you put atoms in each corner, right. So this is BCC and it is exhibited by many metals, like see, these are the examples which exhibit this kind of structure. I am giving you example from the real life. Obviously in real life you will not have this much gap, here it just shown so that it is easy to see, but in real life they will be touching, the spheres will be touching, because we will try to minimize the voids or maximize the density. Okay. Another example is FCC, face centered cubic, right. When you put these atoms, the corners also in the face, on the each face. So, how many atoms are there in this BCC? Because see, in real life you have these unit cells repeating. So, each atom which is at the corner is being shared by 8. So, you can write a formula, total n will be, let us see, if Ni is the inside one, that is not being shared by any other unit cell. The corner was Nc, let us see, shared by 8, right. Let us say Nf, the face, the atom on the face will be shared by only 2. So, this will give you a total number of atoms. So, in BCC you have 2, right. Same thing you can now calculate for FCC. Is it clear how we calculate, right? So, also common packing is FCC, right, FCC packing sequence. So, here we see an atom in every fourth layer lies over the atom in the first layer. So, order is ABC, ABC, ABC. Think of it as like, you have balls, like first layer of A, these are, this is the simplification, you put these balls, then you put B, the second layer will consist of B, which will be on the voids created by A, right. Then similarly you put C, the voids created by B, but then A repeats. So, ABC, ABC, that is the order, that gives you maximum density packing or maximum packing fraction, right. And so, here you see that, right, this is A, B, C, A, B, C, that is how it will repeat. There are only 2 ways to get the maximum density. One is this. So, another way to look at it, look this way, right, same thing, and it is nothing but it is a FCC. If you look at this, you will find out, you have to visualize, this is FCC arrangement, face centered cubic. Another packing, the way of packing is hexagonal closed packing, HCP, hexagonal closed packing. So, in this what happens, you have A, B, so first layer consists like A atoms, then you have second layer of B atoms, the third layer instead of C you have again A. So, A, B, A, B, A, B, that is the sequence, right. It is clear from this picture, this image. So, you see A, then you have B, right, we put void, then you repeat A. So, A, B, A, B, A, B, that also gives you maximum packing fraction. And if you look at the side view, you will realize this is HCP, hexagonal closed packing, and these are the you can see the examples also exhibited by cobalt, magnesium, zinc, zirconium, titanium. Okay. So, this is we are talking about now real crystal structures. So, we will not go much in detail. Now you know what are the different crystal systems, right, Bravais lattices, about the symmetry. Now we will see how can we connect X-rays to crystals, right. So, again little bit of background. So, X-rays, so discovery of X-ray diffraction. So, interaction, it is nothing but interaction between X-rays and crystals, right. So, Laue, Max von Laue was the first one. What he did? Laue, with the help of his experimentalist friends Frederick and Knipping, performed the following experiment. What he did? He put a crystal of copper sulphate was put in the path of a narrow beam of X-rays. Before that, X-rays were known, X-rays were discovered in 1894. So, he just put X-rays before this crystal copper sulphate, which were diffracted by the crystals out of primary beam to form a pattern of spots on the photographic plates, and he had a photographic plate. He saw a very interesting pattern, it had a symmetry. So, that gave the idea that, so this experiment proved the wave nature of X-rays and the periodicity, crystals have again periodicity we talked about, right, the arrangement of unit cells. So, this pattern proved the wave nature of X-rays and the periodicity of the arrangement of atoms within crystals. That is what he did. Okay. So, this is one what he saw. This is the different zinc sulfide, ZNS crystal. When you do X-ray, if you put X-rays, right. So, you see these X-ray refraction spots from the zinc sulfide crystals. So, these were called Laue spots. So, it tells you about some symmetry, right, some periodicity. Okay. So, that for this he got Nobel Prize in 1914. So, Nobel Prize in Physics for his discovery of the diffraction of X-rays. So, this experiment tells you that X-rays can diffract crystals, okay, because you are seeing that periodicity when you put crystals on the path of X-rays. Okay. Here are some transmission and back reflection Laue methods. You can see, you put crystals here, you will see these spots. Another way of looking at is, you let the X-rays go through, and then when there is a reflection you see these spots. Okay. Now, we are not talking about the crystals per se, we only know that X-rays, when they interact with the crystal, give you this pattern. Then around the same time after this came up, Bragg, they found it very interesting. They were reading these papers, right. Laue and with his co-authors wrote about it. There is an interaction between X-rays and crystals. So, they were saying, okay, that is very interesting. So, they did experiments. So, Bragg and Bragg, so basically father and son duo, Henry Bragg and Lawrence Bragg, read Laue's experiment with great interest, right. What they did, then X-ray diffraction was used to solve the structures of crystals. And what they did, they solved the crystal structure of sodium chloride, potassium bromide, potassium iodide. They solved the crystal structure. What is the crystal structure of these compounds? These were the first complete crystal structure determination ever made, and for this they got the Nobel Prize in 1915. Interesting, right? The first one, you see that interaction between X-rays and crystals, then they, with the help of X-rays, solved the crystal structure. Both got the Nobel Prize for their services in the analysis of crystal structure by means of X-rays. Okay. So, now we will see what gives rise to these diffraction, right, diffraction. So, everyone has must have studied this before. We will go over again. The diffraction, what happens? It is basically interaction of two waves, right. So, this is very simplistic example. Suppose your one is consist of 2 and 3, right, waves. If you, and the second ray, for an example, suppose second ray you distort it, and come to B, right, and you look at the resultant will be different, right. So, we are talking about these interference, right. When they will be completely opposite, like, then there will be destructive interference. If they are in phase, it will be constructive interference. So, what does it tell you? Differences in the length of the path travelled lead to differences in the phase, right. So, depends how much difference there is, that will give you the difference in the phase, right. And the introduction of the phase difference produces the change in amplitude, because this phase difference then will affect the net amplitude. Okay. Simple way of understanding this could be, you have two waves, right. So, you have a constructive interference, right. Now, suppose you have this case, right, different. So, here is the peak, then you have a destructive interference, right, because this will cancel out. Clear? Okay. So now let's see, let's look at the interaction between X-rays, and now we are trying to understand, right, the crystal structure, like how can we determine the crystal structure. That's what we will look into. So you have these atoms, right, we are talking about crystals, so there is a periodicity, they are arranged in a systematic manner. So these are the atoms and crystals, right, that's there. Now X-ray will interact, right. So you have this wavefront X dash, that's one wavefront, incoming incident ray beam, right. So let's see, let's consider 1 and 1A in the incident beam. So you have these rays, right, 1A, 1A, 2. So what do you see? 1 will interact with K, 1A will interact with P. Okay, let's look at 1 and 1A first. 1 and 1A means we are talking about only surface atoms, we are not going deep. Clear? P and K. Only in the direction 1 dash and 1A dash. Now you see there is a diffraction in this direction, right. However, are these scattered beams completely in phase? Because they are completely in phase, right, because the difference between these, how do you get the difference? Basically we are QK minus PR. So see, we are looking at this incoming, this is the wave front, right, up to here there is no difference, right. Same thing, beyond this there is no difference between two rays. So only difference is because of this additional QK, this ray 1 travels this much extra, and this travels the 1A dash travels PR, path difference, and you can see from this QK minus PR equals to PK cos theta minus PK cos theta 0. So these two rays are in phase, path difference is 0. Earlier we saw the path difference creates the difference in phase. Phase difference will lead to difference in amplitude, that you know. Okay, so far we talked about the surface atoms, but there are atoms beyond that, like if as you go deep, right. Now we will look at the second layer, B. Now consider rays 1 and 2. Now we are talking about focusing on 1 and 2. 1 will interact with K, let's remove this. Okay. So we are now looking at 1 and 2, okay, and distance between these two layers is D dash, just keep in mind, okay. So what is the path difference for the rays 1 and 2? So 1 interacts with K, okay, 2 interacts with L, and 1 dash is your diffracted ray and 2 dash is your diffracted ray, right. See, up to, let's again similar thing, up to here, if you up to here there is no path difference between ray 1 and ray 2, is it clear? Both are parallel. Similarly, beyond this line there is no path difference. Whatever is, now you have to calculate only the difference. Basically this ray travels this much extra and also this much, right. We are talking about 1 and 2, is it clear? So we have to calculate MLN, ML plus LN, that is the path difference. ML and LN, so what is ML? So you know this is D dash, right, the spacing, and you have angle theta, because incident ray makes theta angle with the plane. So this is theta, right, you can calculate this will be theta using the geometry, okay, because see this is theta, this is 90 minus theta, this is theta. Is it clear? So when this is theta, then your ML will be D dash sin theta, and same thing Ln can also be written as D dash sin theta. So total path difference will be 2 D dash sin theta. It's clear? So now the scattered rays 1 dash and 2 dash will be completely in phase, they will be in phase if the path difference is equal to a whole number n of the wavelengths. That means 2d dash sin theta equals to n lambda, where n equal to 1, 2, 3, right. Basically what we are saying, you have these waves, right. So you have a lambda. Lambda is nothing but this, right. Now, if there is a path difference of lambda or whole number n of lambda, then you will have waves in phase, right. Basically you are shifting, right, by the wavelength, lambda, 2 lambda, 3 lambda. So you will have a constructive interference. So this is the Bragg condition, it is called Bragg's law, right, 2d dash sin theta over n lambda, where n is equals to 1, 2, 3. That gives rise to this constructive interference or diffraction. Again we will look at the Bragg's law. So important to remember is the incident beam, the normal to the diffraction plane and the diffracted beam are coplanar. Okay, this is plane. So incident beam, normal to the diffraction. So this is your incident beam, this is your diffracted beam, this is your normal to the plane, diffracted plane. All three are always coplanar, will exist in the same plane. The angle between the diffracted beam and the transmitted beam is always 2 theta. So how do you get? So you know that this is theta, this angle will always be 2 theta, angle between diffracted beam and the transmitted beam. Okay. Now we know from the last slide that n lambda equals to 2d dash sin theta. Another way of writing it as sin theta equals to n lambda over 2d dash, which is here, right. Now you know that sin theta cannot be greater than 1, you can put this limit, right. So what does that tell you? N lambda over 2d dash is less than always 1. And since the smallest value of n is 1, smallest is 1, right. So what does it give you? Lambda has to be smaller than 2d dash, very important condition. What does it tell you? For most sets of crystal planes, d dash, the spacing is in the order of 3 angstrom or less, okay, for most crystal planes. Hence lambda cannot exceed 6 angstrom, that puts you a limit if you are using a wavelength, right, because you want to know, because you have a range of wavelengths, you want to pick the wavelength which can give you diffraction. So it says your lambda has to be less than 6 angstrom, okay.